So this is day 3 of our chapter 8, our extra chapter on harmonic oscillators. And today we're going to take a look at what happens if there's friction involved in the story with the oscillator. I've got my classic mass on a spring here, and what I'm going to do is just kind of identify right away where my equilibrium position is. So this is going to be the place where if you were to just carefully release it, it would just stay there at that exact spot. Okay, so that could be whatever variable you want to use for position. Maybe it's x, right? So that could be x is equal to 0, where it just sits there. And if you're at that place where x is equal to 0, then at that place you can say, oh, well, then the force is equal to 0 because you haven't stretched or scrunched the spring. And if the force is equal to 0, then at that spot the acceleration is equal to 0. And it would just sit there. But today we're going to look at what happens if this thing is moving along, and in addition to the force from the spring, which tries to get you back to that purple line, what if there's some friction as well? So imagine you catch this oscillator at a moment when it's below equilibrium, but let's say it's heading up. So in green here, I'm going to put in the velocity. Now, as you know from physics, velocity is not a force, right? So in terms of a free body diagram, my forces are going to be the ones that are in red. But I just wanted to highlight that right now I'm catching it at a moment when this thing is actually moving upwards. Since it's below equilibrium, I would have a force from the spring. So that could be this force here. I'll call that Fs for the force from a spring. And it's equal to negative k, the spring constant, multiplied by the position. And here you'd actually have a negative x because you're below the purple line. And if x is negative plus the minus sign in the formula, the spring force would be positive, trying to pull it back up towards that purple line. But if this thing is moving upwards, there would be some air friction on it, right? There would be some drag on it. So the friction always goes against the direction of motion. So my force of friction would be here. And for things that are moving nice and slow, not super fast, it turns out that for slow moving things, it's proportional to, so I'm just going to put in a little constant of proportionality called b. It's proportional to the velocity. Now, as soon as you go fairly quickly, it's actually proportional to the velocity squared. But at the beginning, it's proportional to velocity, or at least for very slow speeds it is. And it's a very useful differential equation to learn how to solve for where it's proportional to velocity. So we're going to start off with that. And speaking of differential equations, let's go and set this thing up. So our classic differential equation is really just good old F net equals ma. But now the net force, I'd have to put those two red forces together. So I would have negative k times x, and then there would be another force minus the bv term. I put minus in there because if the velocity is positive, the friction force would be down, like we see here. But if the velocity is negative, if that mass was going down the page, then the friction force would be back up the page. So it does work really well to put a minus sign in there. So I'm going to say minus, and then this is just this b term there is just a term proportional to that the friction force follows as a proportionality. So I multiply that by the speed, by the velocity, and that is going to equal my mass times my acceleration. But if you think about it, that acceleration, of course, is the second derivative of position. So this variable right there, that's actually x double prime. Now it's useful, not always necessary, but useful if I can get that x double prime by itself. So I have to divide by the mass. And so here's my differential equation. X double prime, the acceleration, is equal to negative k over m times x. We've seen that before. That's our differential equation from the last few pages. But now there's an additional, we call it a damping term, a term that brings in some friction, minus b over m times v. Actually, let's write that instead of v, let's write this as x prime. So I've got the first and the second derivative showing up in my differential equation. This differential equation is something that you will definitely talk about for many days at university. It's a classic differential equation to learn how to solve well, and it has a few different situations. So far, we've been looking at what happens when there is no damping, when there is no BV term, or I guess you could say when the little b there is equal to 0. And that's this picture over on the left. So this picture has no friction. And what we know is the mass will just keep on bouncing forever, at least in theory. But in real life, because of the damping term, right? So this term here Okay, this is what we call the damping term. It's the friction term. It's going to slowly convert all of that energy into heat. Okay, so this is our damping. That's going to gradually pull that mechanical energy out of the system, and it may very well still oscillate back and forth, but the amplitude is now going to be constrained to this envelope, if you wish, this decaying envelope that looks like that green line there. So I'm just going to put decaying envelope. And I say envelope because it kind of captures the motion. The motion has to fit inside that envelope. I just have to learn how to spell. Okay, so this decaying amplitude, I guess, is what I'm saying. So some similarities and some differences between the undamped one and the damped one. So some similarities. What makes them both the same? Well, they both oscillate. Now we're going to talk about some special cases in a minute where maybe there's so much damping it doesn't even really bounce. But I'm going to say that it is going to bounce, so they both oscillate. Turns out they have almost the same frequency. Wow, is it ever close? But there is a big difference. The big difference is, in real life, when there is some friction, the amplitude decays away. So it decays over time. Now we're going to go off on a little aside here for a minute because we're halfway through the notes already. This story about a mass bouncing on a spring, that differential equation up at the top of the page right here, that differential equation shows up all over the place in science, especially in physics and in engineering. It actually shows up for electricity as well. So I've got a picture here that doesn't look anything like a mass on a spring. It's actually two electric devices you wouldn't have seen in physics 11 or 12. There's a capacitor, which are just some parallel plates, and then an inductor. Inductors don't like current to change, and capacitors are like little rechargeable batteries. And I'm just going to go through and show you how this thing can actually oscillate. So right now I don't have any friction. I've got a little resistor here that I'll use in a minute, but right now it's outside of the circuit. So I'm just going to use this battery to charge things up. There might be a brief little fire. Yes, there was. Brief fire. It's all fine now. We're up to our 12 volts. So my capacitor is charged, and I'm just going to let go. I should tell you that that is the equivalent of taking the mass on the spring, lifting it up, and then holding it up nice and high, and then getting ready to release it. So you can see on this graph that it's now up high. That's the voltage on the capacitor. And now I'm going to let it go. The capacitor behaves like the spring, trying to get things back to normal. And the inductor behaves like a mass that doesn't want to slow down or speed up. And so when I let it go, it turns out this thing oscillates. Right? Maybe not super fast, but it does actually oscillate. And it goes back and forth, overshooting equilibrium. Now in this perfect world where there's no resistance, there's no damping, there's no air friction if this was a mass on a spring, that oscillation would just go on forever, right? Just back and forth and back and forth and back and forth. Now I'm going to try to stop it up here near the top of the loop here, top of the cycle, maybe somewhere up around there's probably good. It's pretty close to my 12 volts. And I'm just going to take this little resistor out, or sorry, that wire out, and put this resistor in. Now I don't have a lot of resistance here, and that's actually important for electronics. If I put too much resistance in, it will just decay away without any oscillations. But here, this is what we would call underdamped. And if I connect it, it'll oscillate. It'll go through center. Look, there it goes, right through 0 volts, right? And it's oscillating, but it's not going to stay at a 12 volt amplitude. You can see that it's dying away, just like a mass on a spring with a lot of air friction would. So that's really today's topic, right? What happens if there's some loss, if there's some conversion to heat, and we end up losing that mechanical energy? Here we're losing that electrical energy, right? Converting it to heat coming off that resistor. And you can see it bounced a few times, and now it's still bouncing, but the bounces are so small, they're very, very hard to notice. Okay, just bouncing ever so slightly. We're only going to look at situations like this where it does actually bounce. There are situations in engineering, in electronics, and in masses on springs where you can have so much friction it doesn't bounce. I'll just show you that. So I just cranked that voltage back up on the capacitor. I'm going to change this resistance to something really large. It turns out for this one, around 28 or so is kind of a critical value. I want to go above that to something like 50 ohms and show you what happens. If I go with 50 ohms, this thing won't actually oscillate at all. It'll just decay away and head towards zero. There's so much friction that it doesn't ever really get enough momentum going to get through zero. So this is what we call overdamped. It's kind of unexciting. Critically damped is if you're right on the edge between the two, where it won't actually oscillate, but it decays away about as quickly as you can. This one just really slowly decayed away, and it's kind of just settling out there now on zero. Those are unexciting. We want to look at ones where it's underdamped, where it does actually do the oscillation, where it does this, okay, where it goes back and forth a few times, decaying away before it finally stops. And if you ever go bungee jumping, this is what your ride is like after the big jump. You sit there just bobbing away on the spring, waiting for air friction to slowly slow you down. Okay, so it's a pretty intense differential equation. We are not, for what we're going to do here, try to figure out how you can get to the solution. We're just going to double check that the solution works. So I'd like to show you the solution here. So on the left is just the simple harmonic oscillator, no friction over here, okay? So if you're trying to figure out what's going on this page, this side is no friction, no air friction at all, and this side is the damped one. This is the one that's going to have a friction term. So the differential equation, this one's from last week. We already know this one, negative k over m multiplied by x. Two derivatives later, you're back to position, but you picked up a minus sign and some constants. And we know that we can put that omega in there, square root of k over m, and how great it works. We already know the solution. The solution is actually a combination of cosines and sines. I'm going to sneak that part in here. So you could say, oh yeah, oops, I forgot the amplitude out front. The solution is some number a multiplied by the cosine of omega t plus, if you give it some velocity, some number b multiplied by the sine of omega t. Now we saw that you could actually rewrite that as a single amplitude. We called it d in front of a sine. It was just an option. It was pretty technical, but it did make things a little bit nicer to figure out what the graph was going to look like just at a glance. So those are the solutions to the simple differential equation where there's no friction. And the omega for this story was just the square root of k over m. Now you'll notice that there's a little zero beside this omega. Since we're going to compare the original story to a new one with friction, I'm putting in a little zero, meaning, oh yeah, that was the first one we learned at time zero, day zero when we were doing this. And so we would call this omega naught. That just means at the beginning of the day, at the beginning of the chapter. Okay, so omega naught, just the square root of k over m. And when you're trying to figure out how big that capital A is or how big that capital B is, capital A was just the original position, and capital B was the original velocity divided by the omega. And you were all set to go. The amplitude was nice and steady. It was constant. Once it got going, it just stayed bouncing. And so it was, D, I guess, right, in our combination where we use some trig identity to pack it all together. But now we're going to compare that to the story where there's some friction. So this is a slightly more interesting differential equation. It's negative k over m times x. That's because of the spring. But there's also this friction term, or the resistor term if it's the electronics version. And the solution to this, I gotta tell you, it's intense, right? This is going to be the solution for the underdamped one, the one that does actually do the bouncing, the only one that we're going to look at. It has kind of the same feeling that the old one did, like the A cos and the B sine, but it has this exponential out front that's going to do an exponential decay to decay away. So it ends up being e to the negative b all over 2m multiplied by time So as time goes by, that exponential will decay away. That is going to be out front of the old solution. So let's open up some brackets here, multiplied by, and you're going to kind of see the old solution here now, some number a times the cosine of a slightly different frequency. Like it's amazingly close, but I'll call it omega d, multiplied by time. And that's the first term, but then there's more. There's also the b times the sine of this slightly different omega. It's really close to the old one, multiplied by time. And then we'll close up the bracket on that decaying exponential. So that decaying exponential sitting out here, this is going to affect the entire story. It's going to make the entire thing decay away as time goes by. Now, you can do the same trigonometry that we did before, and you can rewrite this if you wanted to as e to the negative b all over 2m times t. So it's got that exponential decay to it, multiplied by a d, and then sine of a damped omega times time. And just like before, it's a fair bit of work to get there, but it's doable. Okay, the damped omega, the damped frequency. This thing is close to being the same as it was before. It's a square root. It's got a little more stuff in it, though. It has the k over m in there, which I should tell you is usually the dominant term. But there's also a minus b squared all over 4m squared. Usually that's pretty small, so it doesn't affect the story too much, but it is actually there. A is still the original position. B, well, I shouldn't say equals, but B is pretty close to being the original velocity divided by the damped omega. It's off by a little bit, but it's pretty darn close. So the amplitude of the motion, well, the key thing, it decays. There is no constant value to the amplitude. It's actually equal to, that d value that we had in the trig identity combination. But here comes the most important part, multiplied by this decaying exponential, e to the negative b all over 2m multiplied by time. So as time goes by, that amplitude drops off. Now, last little thought here. The damping term b is usually pretty small. So I've mentioned this verbally, but let's put it down just actually in our notes. This k over m minus b squared all for 4m squared. That's usually pretty darn close to the square root of just k over m. K over m is much bigger typically than b squared divided by 4m squared. So my point with this is you might not with your eye notice a big difference in the frequency. There is one there, right? And when we actually go to do our assignment, we'll have to use the exotic version with the b squared on top of the 4m squared. But visually, you're probably not going to notice a big difference. And that's the end. I just wanted to take some time to show you this story of the oscillator that's got some friction and how the motion actually decays away, like you see on that graph on the right. And it's just got that exponential in there that causes it to decay away. That is the story that you'll see in university we call underdamped, right? So it can actually pass through zero several times. If it's overdamped, it never actually oscillates. It just kind of heads towards zero as an exponential decay. But that one's unexciting. So let's just look at this one here. And that's the end of the theory. There's no homework with this particular page. But then next lesson, okay, for the second part of the week, I'll show you what the homework will look like for this half of the chapter. And then you'll have those two assignments, the music assignment, plus this one, which we're going to probably just refer to as the big proof. But we're all finished up here.